So we'll do math instead. 10.4 measures a central tendency. We finished that part of this last time, and we're going to move into variation. We're going to do about half of the variation section today, and then we'll finish up the other half on Monday. The variation part that we're going to start with starts with range. We hear the word range used in mathematics in a couple of different contexts. This particular range is not y values. That's not what we're looking at or something like that from like an algebra perspective. This range is simply talking about how spread out things are from the smallest value to the largest value. So you just take the largest value, you subtract off the smallest value, and that's the range of your data values. Okay? These next few pieces all relate to a graph that we're going to be drawing in a moment. The first one's called the lower or the first quartile, Q1. And it's the value below which 25% or 1/4 of the data lies. So if you can imagine putting everybody, this class is not a good example because there's not enough of you, but pretend you had a whole bunch of people in a line. We talked about last time the median being sort of the 50% mark, right? Well, if you took the first half of the people and you halved it again, you would get the first quartile, and that's Q1. So it's the person below which 25% of the data lies. The middle quartile is the same as the median, the value below which 50% of the data lies. And then the upper quartile is the value below which 75% or 3/4 of the data lies. Or you could equivalently say it's the value that is like the lower end of the top 25%. You could say it from that perspective too, and it would be correct. While we have the range, and it's the difference between the greatest and the least value, we also have the inner quartile range. And what it is it's like the middle 50%. So it's the difference between Q3, the 75% mark, and Q1, the 25% mark. So in a very real sense, this one ends up being Q3 minus Q1. And then the lower extreme and the upper extreme are just the largest value and the smallest value. And then we have the box plot. And the box plot actually shows all these things that we just mentioned in one glance. So you can see the lower quartile, the median, the upper quartile. Visibly, you can see where the IQR lies. You can see the upper and the lower extremes. Box plot is sometimes called a box and whisker plot. So if you hear it used or phrased like that, it's the same thing. And we're going to use that same set of numbers that we encountered last time that have no context, just to practice with. So these were our data values. We do want to list them out in smallest, least to greatest order. So we're going to do 12, 17, 18, 18, 22, 22, and 30. And we found the median last time, and it was the second 18 right here. Now, if the median value is actually a data set value like it is here, then when we look for the Q1 and the Q3, we ignore the median. If we had had a list of numbers where the median lied between two numbers, we would still include everything that doesn't include the median. So the median only gets thrown out if it's actually one of the data values that were there to begin with, right? So I'll create a very simple set, but if this numbers are 1, 2, 3, 4, then the median in between here would be 2.5. Then I would still look at these two numbers and these two numbers to find their medians of those two, okay? So we're looking for Q1 and Q3 now, and what we're doing is we're looking at these data values at the beginning. And again, it happens to be an odd number of data values, so it will be the middle value. If it had been even, we would have found the 2 in the middle and we would have split the difference between them. We would have halved it, right? Found the average of those two. So this value is Q1. This value here is the median. We did call it M, but you can also call it Q2. And then the middle value of the upper three values is actually the Q3. Now you can also see here that this is my upper extreme. Can you guys see this color okay? Okay. It's a little bit light, but... and then this one is over here is the lower extreme. So upper and lower extreme are easy to find. They're just the ending values. So as I create my number line, I really do need to create a number line that's balanced, much like all the other things that I'm doing with graphs. I need to start at the lowest value, go to the upper value, basically make them equally spaced. So we're starting at 12, 13, 14, 15. You don't necessarily have to label each particular point, but maybe every few. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, we'll go one more, 30. Okay. That's a reasonable attempt. All right, so this is just to give a scale. It's really not part of the graph per se, but it's going to be able to give a scale to the graph to make sense of it. So above this number line, we're going to actually draw our graph. So we're going to put a dot somewhere above 12. Give yourself a little bit of space. And I'm going to put a dot at each one of my values. So my next value is 17. I'm just going to put a dot there for now. My next one was at 18. I'm sorry, that wasn't 17. That's 17. The next dot would be at 18. I have 22. And then I have 30. I think they're about at the same height. On the outer edges where we connect to the lower extreme, I'm going to connect these dots, and I'm going to connect them in a very special way. From the lower extreme to the first dot, which is the lower quartile, it just gets connected with a line segment. There we go. And the same thing's true about my upper extreme. Okay? So lower and upper extreme connected with a line segment. In the middle, we're going to form a box. So our box is going to have vertical pieces like this, and they should all be the same height. So I'm going to try and actually... Well, let me just sketch it in and then I'll sketch it nicer. So you have a box that plots these three vertical pieces and then it connects them and makes it into a rectangle. That's not too bad. Yours is probably better. So visually, what is this telling you? Well, that bar in the middle, that's my median. Visually speaking, it splits my data in half, and not half like from smallest value to largest value, but half of the values. 18 and below is my 50% mark. 18 and above is the other 50% mark, right? The part that's in the box in the middle is the middle 25% on each side of the 18, so the middle 50% total of my data values. I can also see how far away the upper and the lower end are from the middle value, how far spread out, and namely how far the range is spread out. And on this, just like every other graph that we've done, we need a title, right? So this doesn't have any actual context. So if you want to just write title in here to remind yourself that whatever the title is, it would still have to go here for context type of questions, which ours would have. We would need that as well. Any questions on that? So this is called a box plot. The other two things that we're going to look at today are distribution values. So the first one's called the mean absolute deviation. The second one is called the standard deviation. They are similar. They're found in similar ways, but their calculations are slightly different once we get further enough in the process. So the mean absolute deviation is the one that comes first. It makes use of the absolute value, namely the absolute in the title, to find the difference each data point is away from the mean. It's found by taking all absolute value differences and averaging them together. So our goal is to somehow try and figure out how far away on average our values are away from the mean. That's what we're really doing. And we're estimating it with absolute values in this case. So we're going to look at one example of that in a minute, but I want to show you all three of the things we're going to look at together, and then we'll find them. The second type of deviation is actually called standard deviation. Okay, so you see that at the bottom of this screen. A portion of standard deviation is variance. So to find the variance, you find the mean, which is what you have to do for mean absolute deviation as well. You subtract the mean from each of your data values, each of your numbers. You square the differences. Okay, with mean absolute deviation, you find the absolute value of the differences. You add the values together, and then you divide by your number of values. With the exception of this step, these are all the same steps as mean absolute deviation. And the only part that's different is the squaring. Instead of squaring, we take absolute values. Okay? And if we had all of that with that square replaced by absolute value, we would have the mean absolute deviation, which I'm going to abbreviate as MAD. Okay? So it would be MAD. It would be the mean absolute deviation if I made that one change. Now that gives you something called variance. But if you take the square root, because you squared things, you actually have the standard deviation. So the standard deviation is basically like taking this list and putting a step 6 on it and saying, now take the square root. And you have a standard deviation. And the standard deviation is actually used in some other things we're going to do on Monday. So that's where we're going to utilize that quantity. Okay, we're going to keep using our just random set of data as we do this. And we're going to find the mean absolute deviation, the variance, and the standard deviation. This isn't the only way that you can do this, but I'm going to strongly encourage you to mirror this because it's a really good way to organize your data and make sure you don't get something lost in the mix, because you're going to be doing a lot of calculations all at the same time, okay, for the problem, that is, anyway. So what I'm going to encourage you to do is to make a table, and in your table, put all of your x values on the far left column. They don't have to be in order, like smallest to largest, but if you want to put them in order, you can. I'm just going to leave mine in the order that it was given to me. So 18, 22, 22, 17, 30, 18, and 12. And last class period, we actually calculated the mean on this, and the mean is actually written as an x with a bar on top, or sometimes you'll see it written as the Greek letter mu, which kind of looks like a combination of a y and a u or something merged together, I don't know. And we found it was 19.9. Okay, so that was our mean last time. So with mean absolute deviation, what we're supposed to do is we're supposed to find the absolute value that each of our x values, that's what these are, they're x values, are away from the mean. So I would grab a calculator, okay? Because some of these are going to be positive, some of them are going to be negative, and I don't want you to actually write down something that's a 0.1 when it should be a 0.9 just because you were moving too quickly. So just double check and make sure you're keeping those things straight. So the first one we're actually doing is 18 minus 19.9. And if you subtract that in that order, you get negative 1.9. But I need it to be an absolute value. So as you're working with these subtractions, it doesn't matter if you do big value minus small value. It doesn't matter if they're positive or if they're negative. At the very end, it's all going to be positive values because they're absolute values. So the distance between 18 and 19.9 is 1.9. Does that make sense? And we're going to do the same thing for every data value. So 22 minus 19.9, that's actually 2.1. And I have a couple of those. 17 minus 19.9 is 2.9. Again, because I'm ignoring any negative signs because it says absolute values. 30 minus 19.9. That one's fairly large given the other values we've encountered. It's 10.1. I already did the 18, so it's another 1.9. And 12 minus 19.9 is 7.9. Is that okay so far? Okay, so we found all the difference between the absolute values and, or we found the absolute value between all the distances or the differences. And then it says that we're supposed to average them together. So you know how to average things. It's the same as finding the mean of something. You add all the values together and divide by your total number of values. So you're going to take all these values and you're going to add them. So you have 1.9 plus 2.1 plus 2.1 plus 2.9 plus 10.1 plus 1.9 plus 7.9. What'd y'all get? what was it? 28.9 is what I have as well, so that's good. Do we have a third? Yeah, okay. 28.9, so then we take the 28.9, we divide by our number of values. How many values do we have? 7. And we will round to 1 decimal place unless something indicates otherwise. So this is 4.1. So my mean absolute deviation is 4.1. Is that okay? So here's the cool thing, and I'll pause while you do it because I have copy-paste abilities and you don't. This table that we've already created, except for the summation part at the bottom, which I'll erase when I get over there, is exactly the table we need to find variance. Okay? So, oh, I didn't mean to cut it. Let's try that again. So when it's asking me to find variance, the first few steps, right, just short of finding the summation here, are the same. And while technically the variance description doesn't say anything about absolute values, step 3 did say I'm supposed to square things. And did you know that when you square things, the signs all become positive? They do. So in a very real sense, I can ignore the signs when I'm taking the difference because when I square them, they're all going to become positive anyway. So this column that I have will match exactly with the column that I need for the other one. And I'll let you draw those in, and then we'll pick up on the next column. Okay, so if you're thinking back to your list of steps, we found the mean, or last class period even. We subtracted the mean from each number and we did this extra sort of absolute value business to it, but it doesn't really matter because on step 3, which is where we are now, we're going to square all those values. So our third column is going to be this x minus x bar, and we're going to square them. So we're going to square all these values. So you're going to go back to your pieces, and you're going to square each one. So 1.9 squared is 3.61. You'll keep all your decimals while we're working until the end. We'll do some rounding. This second one is 4.41, and it's the same as the third. And I have 8.41. Oh, 2.01. Oh, I already did the 1.9. It was 3.61. The last one's 62.41. So that's step 3. Okay. What does step 4 say I'm supposed to do? Find the sum, and then step 5 says divide by my number of values. So it's in a very real sense exactly what we did when we got that 28.9. It's just doing it with the next column over that we just created. So we're going to add together all of these slightly larger values. My sum's 188.87. Okay, seeing some nodding, that's good. So that's step 4. And then step 5 says I'm supposed to do what? Divide it by 7. So if I divide this by 7, it's 20. My calculator says 26.9814. The problem is if I'm rounding to one decimal place, that I can't do 26.9, I'd have to round up. So this is actually 27 if I have to round up to just one decimal place, or 27.0 if you prefer. And that would be my variance. Now, variance doesn't really bear a lot of context for us, but the next step, which is to find standard deviation, does. Okay, so this is my variance. My variance is 27. So variance, I'm just going to write var equals 27. But then on the part C here, where it says to actually find the standard deviation, means I find the square root of that 27. And that number, which is my standard deviation, S is used. The Greek letter sigma is often used as well, which kind of looks like a cursive R or like an O with an extra line across the top. But just so you know, in case you see it, S is what we'll use for standard deviation. And with one decimal, I have 5.2. So it's telling you how far apart things are spread out, 5.2. Compared to when I did the mean absolute deviation, it's telling you things are spread out by 4.1. The calculation is different. The 4.1 has a very good context for us when we're thinking about like distances and things like that. We're going to actually use the standard deviation for another concept later on, though, where it comes into play with normal curves. So there is a further application of this and why we want to use it as opposed to using mean absolute deviation, which is slightly easier to calculate. But standard deviation is actually more useful to us. Any questions? Okay, that's where we're going to stop.